The factors that influence equilibrium are concentration, pressure, and temperature. Let us learn about the effect of each factor in detail. When a system at equilibrium is disturbed by the addition or removal of any reactant or product, Le Chatelier's principle predicts that the position of equilibrium shifts in the direction in which this change is reduced or nullified. The effect of change in the concentration of the products and reactants can be readily known through an experiment. In a beaker, take 20 ml aqueous solution of 0.2 molar iron 3 nitrate. It is pale yellow in color. When 5 ml aqueous solution of 0.002 molar potassium thiocyanate is added to it, the color of the solution changes from pale yellow to red. This is due to the formation of thiocyanate iron 3 ions. The intensity of the red color becomes constant after some time, which indicates the attainment of equilibrium. The equilibrium mixture contains aqueous Fe plus 3 ions, aqueous SCN- ions, and aqueous FeSCN plus 2 ions. The equilibrium constant, Kc, for this reaction can be written as Kc is equal to concentration of FeSCN plus 2 divided by the product of concentrations of Fe plus 3 and SCN-. You have already learned that at equilibrium, reaction quotient Qc becomes equal to equilibrium constant Kc. Hence, you can write Qc is equal to Kc at equilibrium. To understand the effect of change in concentration on equilibrium, let us consider some cases. Adding the reactants Fe plus 3 or SCN- ions to the equilibrium mixture. Removing the reactants Fe plus 3 or SCN- ions from the equilibrium mixture. Adding the product FeSCN plus 2 ions to the equilibrium mixture. Removing the product FeSCN plus 2 ions from the equilibrium mixture. Case 1. Adding the reactants Fe plus 3 or SCN- ions to the equilibrium mixture. Suppose you add a few ml of a solution containing soluble Fe plus 3 or SCN- ions to the equilibrium mixture. You can see that the color of the solution becomes darker. The reaction quotient at this stage of the reaction is given by Qc is equal to concentration of FeSCN plus 2 divided by the product of concentration of Fe plus 3 and SCN- ions. On the addition of Fe plus 3 or SCN- ions to the equilibrium mixture, the denominator value in the expression for reaction quotient increases. This results in a decrease in the value of the reaction quotient. Now, the value of Qc becomes less than Kc. You have already studied that when Qc is less than Kc, the reaction proceeds in the direction of formation of products. That means the reaction proceeds towards the formation of FeSCN plus 2 ions. This is the reason why the solution becomes dark on the addition of more Fe plus 3 or SCN- ions. Hence, in general, we can say that increasing the concentration of any one of the reactants always favors the forward reaction. Case 2. Removing the reactants Fe plus 3 or SCN minus ions from the equilibrium mixture. Now, suppose you add a few ml of oxalic acid to the reaction mixture at equilibrium. You can see that the intensity of the red color of the solution decreases and the solution turns pale. Why does this happen? Oxalic acid reacts with Fe plus 3 ions in the equilibrium mixture and forms a stable complex trioxalate ferrate 3 ion. Due to this, there is a decrease in the concentration of free Fe plus 3 ions in the solution. This results in a decrease in the denominator value in the expression for reaction quotient. Thus, the value of QC becomes greater than Kc. When Qc is greater than Kc, the reaction proceeds in backward direction. Hence, FeSCN plus 2 ions undergo dissociation to give Fe plus 3 and SCN minus ions. Due to the decrease in the concentration of FeSCN plus 2, the intensity of the red color decreases. Thus, we can conclude that removing or decreasing the concentration of any one of the reactants always favors the backward reaction. Case 3. Adding the product FeSCN plus 2 complex ions to the equilibrium mixture. On adding FeSCN plus 2 complex ions to the reaction mixture, the value of the numerator increases in the expression for reaction quotient. Thus, you can say that adding a product to the equilibrium mixture results in the backward reaction. This results in Qc becoming greater than Kc. Hence, the backward reaction, that is, the dissociation of FeSCN plus 2 ions into Fe plus 3 and SCN minus ions, takes place. Case 4. Removing the product FeSCN plus 2 ions from the equilibrium mixture. On removing FeSCN plus 2 ions from the equilibrium mixture, the value of the numerator in the equation for reaction quotient decreases. This results in Qc becoming less than Kc. Hence, the forward reaction of Fe plus 3 and SCN minus ions combining to give FeSCN plus 2 takes place. Thus, you can conclude that removing a product from the equilibrium mixture results in the forward reaction. From the experiment, we can summarize that the addition of reactants or the removal of products favors the forward reaction, while the removal of reactants or the addition of products favors backward reaction. The ability to predict the effect of change in concentration has great commercial application in the cases of reactions where the product is a gas or a volatile substance. Here are 2 examples. In the manufacture of ammonia by Haber's process, high yield of ammonia is favored by the addition of the reactants nitrogen or hydrogen, or the removal of the product ammonia from the reaction mixture. In the large-scale production of calcium oxide, which is used as an important building material from calcium carbonate, carbon dioxide is constantly removed from the kiln, which drives the reaction to completion. Let us now study the effect of pressure change on a system at equilibrium. According to the Le Chatelier's principle, when a system at equilibrium is subjected to change in pressure, then the system tends to shift the equilibrium position in such a direction that the effect is nullified. You know that the pressure of a gas is directly proportional to number of moles of the gas. Hence, the effect of pressure can be easily understood by considering the change in the number of moles between the products and the reactants. This can be made clear by studying three cases. Case 1. When the number of moles of the reactants is greater than the number of moles of the products. Case 2. When the number of moles of the products is greater than the number of moles of reactants. Case 3. When the number of moles of the reactants is equal to the number of moles of the products. Case 1. When the number of moles of the reactants is greater than the number of moles of the products. Consider the gas phase reaction N2 plus 3H2 in equilibrium with 2NH3. In this reaction, 4 moles of gaseous reactants, 1 mole of nitrogen and 3 moles of hydrogen become 2 moles of the gaseous product, ammonia. Suppose the equilibrium mixture is kept in a cylinder fitted with a piston at constant temperature and is compressed to 1/2 of its original volume. As the volume decreases to half, the pressure will be doubled according to the equation PV is equal to constant. As the pressure is doubled, according to Le Chatelier's principle, the equilibrium shifts in the direction of decrease in pressure or the number of moles of the gas. So, in this case, the reaction proceeds towards the formation of the product, ammonia. If you decrease the pressure on this equilibrium, the equilibrium shifts in the direction of the increase in the number of moles of the gas. Hence, ammonia undergoes dissociation to give back nitrogen and hydrogen. Case 2. When the number of moles of the products is greater than the number of moles of the reactants. Consider the gas phase reaction PCl5 in equilibrium with PCl3 and Cl2. What happens when pressure is increased on this equilibrium? In this reaction, the number of moles of gas increases in the forward direction. Hence, as the pressure increases, the equilibrium shifts in the backward direction, which involves fewer moles of gas. Case 3. When the number of moles of the reactants is equal to the number of moles of the products. Consider the gaseous reaction H2 plus I2 in equilibrium with HI. You can see that in this reaction, the number of moles of the reactants and the products are the same, which is 2. As there is no change in the number of moles of the products or the reactants, pressure does not have any effect on the equilibrium. The effect of pressure is important only on those equilibria that involve gaseous substances and not on equilibria that involve liquid and solid phases. This is because the volume and concentration of a solution or liquid is almost independent of pressure. For example, Pressure has no effect on the equilibrium reaction between solid zinc and aqueous copper sulfate to give zinc sulfate and copper, which involves only solid and liquid phases. Now, here is an interesting question for you. Does the addition of an inert gas into a gas phase equilibrium at constant volume result in a shift in the equilibrium? If the volume is kept constant and an inert gas, such as helium or argon that does not take part in the reaction is added, then the equilibrium remains undisturbed. This is because the addition of a non-reactive gas does not change the partial pressure of the other gases in the container.